But atoms and elements, right? Periodic table of the elements, that's what chapter 4 is about. So when we talked about it, everything is made of atoms, right? Everything you look at, everything that you see is made of matter, and all matter is made of atoms. And the atom is the smallest identifiable unit of an element, right? Pure substance for pure substances, elements, can't break them down anymore. And there are about 91 different kinds of atoms, at least naturally occurring. So if you're looking at these periodic tables, actually, all of those ones that are like just the outlines, those are man-made elements in like particle colliders. And generally, they exist for just fractions of a second before they break apart because they're unstable. So atoms are incredibly small. In the first lecture, I told you that in a single grain of sand, there are more atoms than there are grains of sand on the beach, the largest beach. So they are unbelievably small. So as another example of that, if every atom within a small pebble, so take a small pebble, and you took each of the atoms in that and blew them up to the size of the pebble themselves, the pebble would be larger than Mount Everest. If you took, well, we'll get to what a mole is later, but the quantities of atoms that we're dealing with and talking about are insane. They're beyond the realm of just like understanding. We cannot comprehend how many atoms there are even in a single pebble. So the history of the atom and the whole idea is like who first thought of these tiny, tiny things that we can't even see actually goes way back. It was kind of a thought experiment. I am not going to pronounce this right, and I never do. Leucippus? I think it's Leucippus. And Democritus. They are the first recorded ideas of atoms. Or they recorded the first ideas of atoms. And for Democritus, it was, well, if I take a thing, if I take a pebble, and I cut that pebble in half, and I cut it in half again, and then again, and again, and again, at some point, do I run out of things that I can cut in half? And in his mind, he said, yeah, there's got to be some smallest piece that I can no longer cut in half, and that is the atom. And so the atom's name comes from atomos, or indivisible. So it's that indivisible smallest particle. Yeah, I have another example, but it'll be for a later chapter. So that idea, though, was not widely accepted for a long, long time. I mean, a lot of the stuff that we really take for granted today only happened in the last, like, 200 years at most, right? I mean, like, cell phones were invented in, like, the 90s, or, like, the earliest forms of it maybe in the 80s. Computers started in, like, the 50s or 60s, and that's only 70 years ago. Right? And this idea was way back in 460 to 370 BC, so well over 2,000 years ago. So those ideas kind of sat and simmered, and nobody really did anything because what application does it have to everyday life, right? Why does that matter? It's like, cool, you did a thought experiment, there's a tiny thing, whatever, I'm going to go to war now. Right, so it didn't matter. But in the 1800s, so 1808, scientists were starting to work with this theory more, and John Dalton came up with his own atomic theory. And he had been taking different things, doing reactions on a crude level, right? Didn't know what atoms were, but he knew that there were like things in dirt. Actually, I think one of the ones, I think it was Dalton, was isolating urea from urine. So you could take these things, they could like identify that there are these compounds that are unique, and they have masses and all these things. So he put together this atomic theory that each element is composed of tiny indestructible particles, the atomos, the atoms, and that all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. So he took it a step further. He said, okay, so if there's a smallest indivisible particle, there are different types of indivisible particles. So carbon is distinct from nitrogen or oxygen or these other things, which I don't even think they had the periodic table then. But they're unique different types. And so if you have all of one type of an atom, those have the same properties. And those properties will be different from other atoms. And then atoms can be combined in simple whole number ratios to form compounds. So we can stick these atoms together in specific ratios, whole number ratios, to form the compounds that we see and experience every day. So now this is like, all right, what's the practical application of this? It's like, well, if we can understand these things, maybe we can manipulate them. Maybe we can create things that otherwise wouldn't be created, or understand our environment better. Now we've got some practical application to the idea of the atom. So scientists in IBM, we saw before, Japanese character under a scanning tunneling microscope, but this is the words or the letters IBM, placed there by IBM, and these are xenon atoms. So the cone shape is because of the way that they're imaged. They're actually spherical in general. So we have ways now that we can kind of visualize these atoms. So moving on, we have now sort of this general idea that these atoms are maybe, in the crudest form, just like hard little spheres. They're like marbles, right? So you got different types of marbles. You get your catis, you get your clearies, you got your steelies, you know. I don't know if you guys played marbles in junior high. We did until they took them away because kids were fighting because they were gambling their marbles. So until J.J. Thomson came along, I'm sure people had their different theories, but he put together this idea along with this particle he discovered, a smaller particle called the electron. And the electron has a negative charge. And so his theory is that now our atom is actually, does it say plum pudding on here somewhere? Yeah, the plum pudding model. So plum pudding is not like what we think of pudding. It's British pudding. It's more like fruitcake. So the electrons are like little pieces of fruit in a fruitcake suspended inside of a sphere. So these electrons are part of the atom, but they're stuck inside of it in this sphere. And they're uniformly present in many different kinds of substances. So a lot of things have electrons. And his theory, part of his theory too, is that they were held in a sphere of positive charge, which balanced the negative charge of the electrons. So this is going to be a common thing, balancing charges. Everything that's on the periodic table, balanced charges. But we'll get to the periodic table more. So moving forward, scientists are still trying to figure out what exactly is the structure of an atom. Is it a plum pudding model? Is it a tiny little cake? And Ernest Rutherford did an experiment, the gold foil experiment, where he directed tiny positively charged particles called alpha particles. So it's a result of radioactive decay. And he shot those through a very thin sheet of gold foil. Most of the particles passed through the foil, which was what you would expect for something like a plum pudding model. There's no real solid mass to it. There's not, it's not solid. So if you fire charged particles through it, they should pass right through. Maybe they'll knock off some electrons or something, but they'll travel in a straight path. In Rutherford's experiment, not all of the particles passed straight through, which was completely unexpected. Some of them were deflected at sharp angles. This is the experiment here. Has some source surrounded in lead, firing the charged particles through the foil. Most of them ended up being detected over here. And then this is like a it's like a special film, and it lights up when it gets hit by the charged particles. So that's how he's detecting where they're coming off. Some of those particles bounced back. So again, getting to the plum pudding model, no solid mass to it. Everything should just pass straight through. Nothing should be bouncing back. I love this quote. So the result that some of these particles bounce back, Rutherford said, is about as credible as if you had fired a 15-inch shell, cannon shell, at a piece of tissue paper and it came back and hit you. So that this foil should have been like tissue paper to these charged particles, should have blown right through it. But now they're bouncing back. So he's like, we need to revise our thinking on what an atom actually is. And so we went from the plum pudding model to the nuclear model. Now instead of having, I'm going to use this picture. It's on the next slide. So now instead of having this sort of nebulous positive charge with negative charges stuck inside of it, we have a solid, very, very tiny, very dense positive charge at the center and a cloud of electrons around it. So these charged particles were hitting that tiny, dense center of some of those atoms, and that was what was deflecting them. The ones that passed through went through these empty electron clouds around the nucleus. So most of the atom's mass and all of its positive charge, so most of the mass and all of the positive charge is contained in a small core called the nucleus. Most of the volume is actually empty space. That applies. So this is our best model now for the general structure of an atom. And everything around us, it's made of atoms, is mostly empty space. And the reason we can't pass through it is because of those electron clouds. And so that negative charge in an atom is in the empty space around it. And so the electrons are dispersed in there. And again, this is going to come up a lot. The number of negatively charged electrons outside the nucleus is equal to the number of positively charged particles, which are called protons, inside the nucleus, so that the atom is electrically neutral. So the number of electrons in a neutral atom is equal to the number of protons. Oh, I guess we got to add one thing here. So later work discovered that the atom's nucleus has positively charged protons and some neutrally charged neutrons. So more than 99.9% of the mass of an atom is in that nucleus, that central core where the protons and neutrons are. And then there's a cloud of electrons around it. So now I've got all three of the, is it over here? Yeah, okay. All right, so we've got protons, neutrons in the nucleus. Almost all the mass is there. The electrons do have a tiny amount of mass. But that gives us our three sort of fundamental particles or pieces that make up every atom. So we've got protons and neutrons, which have very similar masses, and then electrons, which have almost negligible mass, or it's so small you can almost ignore it. These masses in kilograms, again, remember, atoms are tiny, so the particles that make up atoms are even smaller. These masses are not practical to use in grams or kilograms. So in terms of kilograms, a proton weighs 1.67 times 10 to the negative 27 kilograms. So very, very tiny masses. So when we're talking about atoms and their mass, they came up with a new unit called the atomic mass unit, an AMU. And they define that as 1/12 the mass of a carbon atom that has 6 protons, 6 neutrons. So now it makes it a lot easier. One proton then has an AMU of 1. One neutron has an AMU of about 1. Again, they're slightly different. And then electrons are 0.00055 atomic mass units. So it's at 5/10,000ths of the mass of a proton or neutron. So if a proton had a mass of a baseball, the electron would have the mass of a single grain of rice. So that's about how different the masses are between them. So we talked about like why is matter solid? Because again, most of matter is empty electron clouds around solid nuclei or cores. So if you could zoom in far enough, then you'd see the spaces between those atoms. But yeah, generally we can't see that because those spaces are so tiny and because of the way light bounces off of those electron clouds too. Yeah, 929, perfect. All right, so the electrical charge is a fundamental property of protons and electrons. We want positive charges, negative charges attract each other. So opposites attract. Like charges repel each other. This is part of why atoms don't just pass through each other, because it's a dense core that's positive, surrounded by negative charge. And so when that negative cloud bumps up into a negative cloud, they repel each other. And then positive and negative charges, this is super important, positive and negative charges cancel each other. So if we add a positive charge to a negative charge, the overall charge is going to be 0. So every proton is a positive 1. Every electron is a negative 1. Positive 1 plus negative 1, 0. Actually, before we go to that, so when I'm having you memorize these, actually no, maybe we need to talk about this first. We'll talk about it on this slide. So the number of protons is what determines the identity of an element. And so the number of protons for an element never changes. The only thing that changes is the number of electrons. So I'm having you memorize these lists of elements and the one type of charge that they form. That's because they're either losing an electron or they're gaining an electron. And we'll get into more of why they do that, but for now, just memorize it. So the number of protons is what identifies the particular element. So actually on the periodic table, the number on the top right is the number of protons. So every carbon atom has 6 protons. Every nitrogen atom has 7. If you add or remove protons, you change the identity. And the atomic number, the atomic number is that number in the top right corner on the periodic table, is represented by Z. So the atomic number is Z. So it's just another periodic table. We'll get to atomic mass in chapter 4, but we're given the chemical symbol, which you guys have been memorizing, and their associated names, and then the atomic number, sometimes in different places on the periodic table, but that's going to be Z. And so again, just had you memorize these, because there's really not anything to do other than memorize the symbol and name combinations. Some of them are just the first letter of the element. Other ones are 2 letters. There are never more than 2 letters for element symbol. And those are just abbreviations of the names. The few that are really weird are based on the Latin, was it Latin or Greek names for them? So potassium is K because its historical name is callium. And sodium is Na because its historical name is natrium, lead is plumbum, and so on. The element of surprise. That one's AH. So what is the name for Na? Sodium. What's its atomic number? 11. Well, what charge does it form? Yeah, sodium always forms a +1 charge. What is Ni? Ni is nickel. This is now on the list of ones that I had you memorize. So it's nickel, its atomic number is 28. Nickel will form multiple types of charges. I actually don't know what they are. It doesn't come up very often. What's P? Phosphorus, yeah. And its atomic number? 15. What's Ta? It's tantalum. Yeah, that one's harder. And on these periodic tables, they don't have the, which I think is named after Tantalus, which is some Greek mythology thing. I can't remember what his deal was. 73, yeah. And so then, because I think Tantalus is where we get the word tantalizing. So I'm sure it has something to do with that. All right, so you probably maybe you've wondered, maybe you haven't, why is the periodic table this shape? It's actually because there are a lot of things that can be predicted from the order of the elements on the periodic table as it is. Now, we'll talk more about how it really does come down to the electrons for each element. And I'll plant this seed right now, but how many electrons does hydrogen have in neutral hydrogen? No charge. One. How many electrons does helium have? Two. Lithium? 3, 4, 5, 6, 7, 8. So the neutral charge is also the number of electrons. The way that those electrons interact with other elements actually determines the properties of the element. So they react the way they do because of the numbers of electrons that they have and the way that those electrons arrange themselves around the nucleus. So the periodic table, one of the big things that the periodic table shows you is that actually for those first three, well, the second and third row, there's 8 elements there. And that's a special number for atoms. They like to have 8 electrons, right? So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. That's 8 elements across. So it was Dmitry Mendeleev who figured all of this out. He was just looking at, like, how should we arrange all of these elements? Should we just make it a list of the number of protons from 1 to however many they had at the time, which they probably only had these 20, or increasing mass or certain sets of properties. He figured out when you arrange them in this way that everything in group 1 has similar properties. And basically in every column on the periodic table, those elements have similar properties to each other. So we'll look at some of the patterns on the periodic table, and you should definitely be using patterns on the periodic table to help you remember things like charges or reactivity, those kinds of things. The periodic tables, these ones aren't broken up this way. but generally have the elements shaded by what class of element they are. So most of the periodic table, so below hydrogen and then down here, most of them are metals. So they're going to be metallic in nature. Right? We know what metals look like. They're shiny. They generally conduct electricity. They're usually malleable, so you can bend them. Then we have a few elements that are metalloids. So they have some properties of metals, some properties of nonmetals. And then you're actually probably pretty familiar with nonmetals as well. Things like carbon or water is made up of two nonmetals. They're generally brittle. A lot of them are gases. And all the nonmetals have similar properties. All the metals have similar properties. And the metalloids even have similar properties to each other. So actually, and it's no accident that arranging the periodic table this way groups those similar elements together. They didn't like test all of these elements for their properties and then place them on the periodic table so those lined up. They lined the elements up based on the number of valence electrons, which we'll get to later, and all of the metals ended up in a group. All the nonmetals ended up next to each other, and all the metalloids ended up next to each other. So that is a just result of organizing the periodic table this way. So here's more of the properties of metals. Again, good conductors. They're malleable, so you can pound them into flat sheets. They can be drawn into wires, which is called ductility, and they're often shiny. And then this is actually, I think, the most important property for you guys to remember, is if something is a metal, in this class especially, if something is a metal, it's always going to lose electrons and have a positive charge. Metals always lose electrons and form positive charges in this class. There are edge case things where they can have negative charges. That's not going to come up. So I never want to see you write down a metal with a negative charge. So that's most of the left side. Iron, magnesium, chromium. Nonmetals, that was that group in the top right corner. They're going to be, well, some are solids at room temperature, others are gases. They tend to be poor conductors of heat and electricity. And again, just like metals lose electrons, have positive charges, nonmetals gain electrons when they undergo chemical changes and will have negative charges. So remember, the number of protons doesn't change. So the only thing that changes is the number of electrons. And I know it can be a little bit confusing because it's a little bit, it feels backwards because we're adding negative charges. But if we have oxygen, for example, how many protons does oxygen have? 8, yeah. 8 protons, and protons have positive charges. So oxygen likes to lose 2 electrons. So neutral oxygen will have 8 electrons, so those are balanced. But if oxygen loses 2 electrons, now it's got 6 electrons, what charge is that oxygen going to have? Oh, sorry, gains electrons. My bad. Sorry, gains 2 electrons. Yeah, it's going to be 2 minus. It's because we have a negative 2 charge, or 2 minus charge. So this would be 0 charge. And yeah, I should write it like this, because it's supposed to be 2 minus charge. All right, so it's the number of electrons that changes. So nonmetals should always have negative charges. The metalloids are weird. On these periodic tables, they're just the ones along that red zigzag line. They have some properties of metals, some properties of nonmetals. And the semiconductors are in there. So silicon, right? Silicon's what powers all of our computer chips. All of our technology is powered by silicon. It's a semiconductor. So you can change whether or not silicon will conduct electricity, well, by passing a voltage across it. So if you fill in, I'm not going to get into it because I don't understand it all that well. But basically, you can modify the properties of silicon, and so it acts like a gate. You can basically turn it on or off, whether it's conducting electricity or not conducting electricity. So yeah, silicon, arsenic, there's not very many metalloids. All right, so is sulfur a metal, non-metal, or metalloid? Non-metal. Is sulfur going to form a positive or a negative charge? Negative charge. How about chlorine? Could be a non-metal again. And we can figure out that's a non-metal because of where it is on the periodic table. You'll be given periodic tables on all your exams, and because it's a non-metal, it's going to form a negative charge. And then how about titanium? Metal. It'll form a positive charge. How about antimony? SB is antimony. What was that? Metalloid. It's a metalloid because it's right on that zigzag line. Positive or negative charge? I don't know. It could be either. It's a metalloid, so it's right on the cusp of being a metal or a non-metal, so it'll depend on the situation. Okay, well, that's 9:45. Excellent progress, though.